This instructional video explains how to calculate the stresses and strains in thin-walled, non-circular tubes when they are subjected to torsional loads. What are the thin-walled tubes? In mechanical engineering applications, thin-walled tubes refer to hollow tubes with relatively small wall thickness compared to their overall diameter. These are not necessarily bicircular. These tubes are commonly used in various industries due to their lightweight nature and efficient material usage. Let us now consider the cross-section of a thin-walled non-circular tube as illustrated here. The thickness of the wall is taken as simple T, and it varies along the periphery. The thickness at point A is T1, and at point B, it is T2. Also take the length of the element shown here as delta L. If F1 and F2 are the shear forces acting on the two surfaces, along the longitudinal direction, for the equilibrium of the element F1 should be equal to F2. F1 and F2 can be written in terms of shear stress, toe, thickness, and the length. At any point, the term shear stress, toe, multiplied by the wall thickness, T, is called as shear flow, and it is denoted by Q. Therefore, we can write Q1 into delta L is equal to Q2 into delta L. This means Q1 equals Q2. This means, along the thickness of the tube, the shear flow is constant. Let us now derive an equation to calculate the shear stress when a thin-walled tube carries a torque. Figure here illustrates a cross-section of a non-circular tube. Its center of area is given by O. D, E said, is an elemental length on the periphery. NQ is the direction of the shear stress. Simple H is the perpendicular distance from the center of area, O, to the line, NQ. The length D, E said, subtends a small angle on O and creates a small triangle OPQ as shown. The torque due to shear force on the element PQ can be written as shear stress into small area, that is given by thickness into d SAd, multiplied by the normal distance to the line of action of the force, H. The total torques is found by integrating over the periphery of the tube. Therefore, the total torque is equal to shear flow multiplied by the integration of H into d SAd. The area of the small triangle OPQ can be written as dA equals to half H into d SAd. By substituting for the integration of H d SAd, we can simplify and obtain an equation for the torques with the shear flow and the enclosed area, A. Then, the shear stress is equal to T divided by 2AT. This is known as Brett-Batho formula. Next, we look at how to calculate the angle of twist in a tube when it is subjected to a torque. To calculate the angle of twist, we can use the general Trojan formula used for solid cylinders with the equivalent polar moment of area. This polar moment of area takes into account the specific properties of the thin-walled tube. Therefore, our next step is to derive a formula that can be used to find out the equivalent polar moment of area. To do this, we use principle of energy conservation. That is, the strain energy stored in the tube due to the elastic deformation is equal to the work done by the applied torque on the tube. We can readily say that work done is the half of torque into angular twist. The strain energy stored in unit volume, simple U, is given by the half shear stress, τ, multiplied by the shear strain, gamma. If the modulus of rigidity of the material is G, the shear strain, gamma, can be written as τ divided by G. Therefore, the strain energy per unit volume is written as τ squared divided by 2G. The total strain energy is then calculated by integrating τ squared over 2G, multiplied by L, T, d SAd, over complete periphery. With the substitution τ equals Q over T, the total strain energy, U, is evaluated as Q squared into L, divided by 2G, into integration of d SAd over T. Now, we can equate the expressions for the work done and the total strain energy. Rearranging the terms, we obtain an expression for g(θ over L). Since g(θ over L is T over J according the torsion formula, we replace g(θ over L by T over J. Then, J can be written as T squared divided by Q squared into integration of d S8 over T. Now, we substitute for T equals 2QA. Finally, J is obtained as 4A squared divided by the integration of d S8 over T. If the thickness, T, is uniform over the periphery, the J is simplified to 4Ta squared, divided by capital ASAD. Here, ASAD is the perimeter of the section. Let us look at an example of a section having different wall thicknesses. In the figure shown here, the thicknesses are T1 and T2 for the sides of the section. Then, we calculate ASAD over T for each part and add all of them. Once J is calculated, the angle of twist can be found from the general torsion formula, that is θ over L is equal to T over Gj.